Welcome to the third part of the webinar regarding the TRACE32 integration for Simulink and the TRACE32 AUTOSAR awareness. In the third video, a processor-in-the-loop simulation will be performed in order to verify that the generated C code is executed on the embedded target hardware in the same way as previously predicted by software simulation. In order to verify a Simulink model on the embedded hardware, first of all the ASWC block of the original model has to be replaced by the recently generated PIL block. This PIL block has been created by use of the TRACE32 integration for Simulink and accomplishes the interaction with the TRACE32 debugger. The PIL block is fed with input data generated by the Simulink source blocks. It transfers this data to TRACE32 PowerView, which writes the data to the embedded hardware via the debug interface. Then the embedded system executes a single calculation step of the algorithm generated from the model. This means that the generated code is not executed in real time but step by step. After each single step, the calculation results are transferred back to the PIL block's outputs in order to display the data in the scope blocks and to write it to a MAT file. Before the PIL simulation can be started, one last action is required. In the library browser, the TRACE32 setup block is available. It has to be added to the model. The block stores soft and hardware related information which is important for a correct startup of the TRACE32 debugger. The most important settings are the target hardware's architecture and its exact CPU type. The Integration tab offers the possibility to specify a special working directory or special target binary type. In this demo and in most other cases, these settings are auto-detected and therefore can be omitted. In the Scripting tab, a startup script suited for the target hardware has to be specified. Therefore, the default setting has to be changed. The startup script is written in practice, the TRACE32 scripting language. The script contains some basic commands like the system reset, the CPU configuration and the loading of the target binary file. Moreover, the script contains a hardware-specific setup of the memory management unit. All settings are confirmed by clicking the OK button. Before the PIL simulation can be started, it is required to save the model. A new name is specified in order to preserve model ASMulti.mdl with the original ASWC block and its subsystems. The scope block and TRACE32 PowerView are brought to front in order to see the progress of the PIL simulation. After clicking the Run button, activities can be observed in all windows. The scope block displays the results calculated on the embedded hardware. The MATLAB comment window as well as the status bar of the Simulink model display the simulation progress. TRACE32 displays the various system states of the embedded hardware. Now the Simulink model has transmitted all input stimuli, but the embedded system is still waiting for further input data. By clicking the break button, the software execution on the target hardware is stopped. This is a suitable moment to have a closer look at the TRACE32 system. The software release is August 2013. The debug hardware is a PowerTrace USB 2.0 module. Its trace functionality is not mandatory for use of the TRACE32 integration for Simulink, so a power debug module would also be sufficient. A closer look at the source code of the PIL integration reveals that the communication between the embedded system and Simulink is done by 4 simple functions. The function prototypes are specified by the MathWorks PIL framework. Later on we will have a look at the corresponding C file. Next we will have a look at the navigation feature. The functions generated from the subsystems of the Simulink model as well as all other symbols are known by the debugger. We will have a look at runnable two-step. Most commons contain a navigation tag. By right-clicking on this tag, Navigate to Model can be selected. Because the original ASMulti.mdl model is not open yet, it is opened automatically and the corresponding block is highlighted. Also, the higher level blocks are highlighted. A general TRACE32 control menu can be found in the Tools menu. It offers a breakpoint control, download dialogues, setup options and a version information. Because only model ASMulti.pil.mdl is connected to TRACE32 at the moment, a new connection has to be established. Now it is possible to open a block context menu by right-clicking on the block and to display the corresponding code in the TRACE32 debugger. Because the generated source code of the integrator block is located at more than one location, 3 data list windows are opened. At the top lines of each window, the navigation tag for the integrator block can be found. Among the files contained in the folder TRACE32pil, there's a C file. This C file implements the 4 pil communication functions on the embedded target side. We already inspected these 4 functions with the TRACE32 debugger. The DLL file is loaded by MATLAB. It realizes the pil communication at the PC side. At the end we will verify that the recorded data of the hardware simulation, which has been shown in this video, and the recorded data of the software simulation, which has been shown in the previous video, are concurrent. This is done by loading both data records and by displaying the difference of the data values. One can see that there's no difference, so the generated code works as intended.